Okay, if a system is commutative, then you should be able to switch up the orders of two operations, and you would get the same thing as if you just kept it in the original order you had it. So an example of if this operation was commutative would be that you could say 3 operation with A is the same thing as A operation with 3. We can switch their order, but we get the same thing. So let's check that real quick. Let's see if that's true for 3 and then the triangle operation in A. So if you start with 3 and you match it up with A, that gives us 5 for a result. So 3 in the row, A on the column gives us 5. Now let's switch that. Let's do 3 on the column, A on the row. If you switch those up, you also get 5. So far it looks like it's commutative. But for it to be commutative, we'd have to check every single pair. So we've got that 3 and A are commutative. We want to check 3 and 5. So 3 triangle 5, we need that to equal 5 triangle 3. If it doesn't, we say this isn't commutative. So 3 triangle 5 gives us A as a result. When you match those up, the row and the column gives us A. Now if we swap them, I'm trying to get rid of that circle, there we go. Okay, so if we swap them, if we do 5 on the row and 3 on the column, we also get A. So it's looking good. Now we should pair up 3 with K. So 3 in the row, K in the column gives us 3. And then if we go K on the row, 3 in the column, that also gives us 3. And what else haven't we paired up? We haven't paired up A and 5. You'd have to go through each list. Sorry, each possibility. So there's a lot there, but I think it's going to be commutative. Because A and 5 is the same thing as 5 and A, right? A and 5 gives us 3. 5 and A gives us 3. A and K, so A on the row, K on the column gives us A. K on the row, A on the column also gives us A. And then 5 and K, if we partner those up, 5K makes 5. K, 5 makes 5. So it is commutative because you can switch up the order, you get the same thing. If it's associative, that means you could swap the grouping and you still get the same thing. So an example would be that 3 triangle A with parentheses around it, meaning we got to do that first, and then triangle 5, that should be the same thing as 3 triangle parentheses A triangle 5. Okay, so let's check that out real quick. If we do 3 triangle A, 3 in the row, A in the column, it gives us 5. And then 5 triangle 5 gives us K. So the left side is K. Let's see if the right side is also K. So we got to do parentheses first. So A triangle 5, here's A, and then here's 5. That makes 3. And then what's 3 triangle 3 according to our table? 3 in the row, 3 in the column, it gives us K. So they match. This is the same thing as this. And now that's one particular example. You'd have to go through every possible example to make sure that it's associative. If it even fails once, it's not associative. So I'll leave that. Well, that's like an impossible task. There's too many. We could just do one more just to check. K, triangle. Let's throw in another one. 5 triangle A. That should be the same thing as K triangle 5 triangle A. So real quick, 5 in the row, A on the column. 5 and A gives us 3. This is 3. And then K on the row, 3 on the column gives us 3 for a result. That's what this left side is. K triangle 5. So K on the row, 5 on the column gives us 5. And then 5 triangle A, 5 on the row, A on the column gives us 3. So it's working. It looks like it's going to be associative. Took us a lot of work to get there, though, didn't it? I'm not sure how Newton's got this set up because a student would have to go through every possible combination, which is it's not feasible. If A is an identity, that means you should be able to put, that means whatever you put into A, it should always spit itself back out. So if you do like 3 triangle A, should give you 3. If you do 5 triangle 5 triangle A, should give you 5. Because an identity means you don't change it, right? So here's A, here's 3. You line those up, A in the column, 3 in the row, that spits out 5. If A was an identity, then it doesn't matter what you match up, it should always spit out whatever you're putting into it. So A is not an identity. Is K an identity? So that means 3 triangle K, we expect that to give us 3. That means 5 triangle K, we expect that to give us 5. 3 in the row, K on the column gives us 3. So it's working so far. 5 on the row, K on the column gives us 5. It's working. So K is an identity. A and 5 are inverses. Myself on something that I hadn't seen in a while. If this square here is symmetrical about the diagonal, then it's commutative. So that's not a real mathy way of being sure that it's commutative, because that's not really using the definition of commutative, but it sounds like that's a quick trick to find out whether it's commutative. If you get the same thing, like if you split it on the diagonal and you get the same thing on the bottom left as you do in the top right, then it's commutative. And it looks like it, right? There's A's, D's, and B's that are directly across from each other. These C's, these E's, and these D's are directly across from each other, so it looks commutative. So because we have an option, it's either a group or commutative or both. For it to be a group, it needs to be closed, which means every element in the rows has a chance of pairing up with every element in the columns, and it does, right? A connects with B, A has a chance of connecting with C, and A has a chance of connecting with D. So if you have A, B, C, D in the row, you've got to have A, B, C, D somewhere on the columns. So we're good. It's closed. For it to be a group, it needs to have an identity element, which means it's one element that always spits out whatever you pair it with. So let's see. It looks like it might be A, because no matter what you do with A, no matter what you pair it up with, it always spits it back out. A paired with B gives you B. A paired with C gives you C. A paired with D gives you D. So A is the identity element. So there is an identity element. Let's see, what am I forgetting? It's closed. It has an identity element. It's commutative. Invertible, the identity element needs to be in every row and in every column. And that's not the case. We have A, the identity element, in this first row. We don't have A in this row. So it's not invertible. Okay, that's a quick trick, and we talked about the inverse in another video like these two. But a quick trick for finding whether these are invertible is that identity element that we pick out earlier needs to be in every row and in every column, and that's not the case here. So that means it's not a group because it's not invertible. There's an identity, but not every element has an inverse. Question, because currently as of this video, Newton has this programmed incorrectly. It has the wrong answer programmed. Newton says that D is the identity element, but it's clearly not, right? Because if you pair A with D, gives you D. If you pair if you pair B with D, gives you E. That's not an identity element at all. So Newton has something incorrectly programmed. Newton's incorrect answer right now is it is a commutative group. Okay, but hopefully they'll have it fixed by the time you run into this question.